Hello, so my name is Devansh and I have created this presentation on the fast Fourier transform algorithm with my two group members, Anirudh and Saud. So I'm going to start with explaining the topic, that is fast Fourier transform algorithm. So understanding fast Fourier transform by polynomial multiplication. We are going to understand this algorithm by approaching it with polynomial multiplication. So consider that you have got two polynomials and you want to multiply these two polynomials. Now, the basic way in which you would follow this operation is by actually using algebraic arithmetic and multiplying each term of the first polynomial with the second polynomial, right? And you would get the answer, right? And that would be the standard way of computation, right? So before we understand how are we going to actually understand the algorithm, we need to understand how do we represent polynomials in computers, right? So we represent polynomials in computers as coefficients in an array. For instance, this array of 2, comma 3, comma 1 represents coefficients of different powers of x that are present in the polynomial. So this is um, coefficient 2 that is in multiplication with x to the power 0. That's why it is present at the 0th index. This is 3, which is multiplied by x to the power 1. That's why it is present at the first index, right? This is 1 multiplied by x to the power 2. That's why it is present at the second index, right? So similarly, we represent polynomials in terms of arrays, right? So essentially, what do we say is that C of k is the coefficient of kth degree term of a polynomial, right? C of x. Therefore, we call this as a coefficient representation of a polynomial. Now, let's consider a general case. We've got two d degree polynomials, that is a of x and b of x, and we want to multiply these two polynomials to get a third resultant polynomial. The running time of this algorithm using distributive property that we used, that was the standard approach, the standard algebraic approach. The time complexity was O of t squared because remember you are doing how many operations you are doing. You're multiplying this term with every term of the second polynomial, then this term with every other term of the second polynomial. So you're performing this d squared times, right? Now the question is how can we reduce this time complexity? So let's come back to polynomial representation again, right? So let's say that you've got a straight line. Now that straight line can be represented by two distinct points, that is these 2 points, right? Any straight line geometrically can be represented by exactly 2 points. If I extend this idea further to higher degree polynomials, for a polynomial with power 2, the highest power 2, you can represent it uniquely with 3 points, right? So if you have three distinct points plotted on a certain 2D plane, you can represent those 3 points with a certain polynomial, right? Because even if you consider the most basic example, that is this straight line, the equation of straight line is y is equal to mx plus c, right? Mx plus c. Now c is obviously the y-intercept, m is going to be the slope, right? And the slope is determined by 2 points, that is y1 minus y2 upon x1 minus x2, where x1, y1, x2, y2 are 2 points. Similarly, uh, 2-degree polynomial can be represented by 3 points. Now, in general, I can say that any polynomial of degree d can be uniquely represented by d plus 1 distinct points. As I said, a straight line is in form of mx plus c, right? It's a 1-degree polynomial uniquely represented by 2 points. Similarly, if I have a 2-degree polynomial, it can be uniquely represented by 3 points, right? So it's a 2-degree polynomial represented by 3 points. It's a 1-degree polynomial represented by 2 points. Therefore, in a general case, I can say that any polynomial of degree d can be uniquely represented by d plus 1 points, right? So I can say that, okay, this is the d degree polynomial, and these are going to be the d plus 1 points of that d degree polynomial, right? Now, what I'll do is I'll just represent these each of the y coordinate of every point in terms of this polynomial expression, where I'm just substituting this x naught value in the polynomial expression to actually get the y value. Okay. Now, this system of equations can be represented by a matrix product like this. Okay, a dot product, a matrix dot product of sorts, right? Where x naught, x1, x2, all of these are input x coordinates in the 2D plane, and these are, then multiplied with the coefficients. So we are taking the dot product of these points with the coefficients, all the coefficients, to get the resultant y value, and you're getting each y value of every point like that. Now, this matrix that I've got here is invertible if and only if unique values of x naught, x1, x2, and xd exist, right? So this matrix is invertible only if unique values of x naught, x1, x2, and xd exist, right? So if any 2 points here, if any two rows are the same, so if any 2 points are the same, then any two rows would be having exactly same values, which means that by elementary row transformation, I can reduce this matrix to having a zero row, right? And if this matrix has a zero row, that simply means that its determinant is zero. And if the determinant of any matrix is zero, then it is not invertible. Okay, so it is important for all these points to be distinct so that this matrix is not invertible. So that this matrix is invertible, right? So if any of the two rows are same, then the matrix is going to be not invertible. And why is it important for the matrix to be invertible, right? Why is it important for the matrix to be invertible? It is because for these b plus 1 points, there exist unique coefficients, okay, which give you a unique polynomial p of x, okay? That's why this is important, that the matrix is invertible.
So yeah, in this FFT slide, we are going to see that how FFT can be used to efficiently multiply two polynomials by converting between the coefficient and the value representation. So in this slide, we are given two polynomials. A of x is equal to x square plus 2x plus 1 and b of x is equal to x square minus 2x plus 1. So if you want to compute ax dot b of x, note on the degrees. Multiplying a 2-degree 2 polynomial results in a degree 4 polynomial. Therefore, we must note that 5 points should be used to determine the result. So to multiply two polynomials, we can either convolve their coefficient, which is a slow process as it will take a complexity time of O(n) square, or else we can evaluate both at enough points and multiply the values and then interpolate, and thus FFT is faster than other methods. Now we would like to move on the next slide, that is the points at which both the polynomials are evaluated as shown. Ax is evaluated at minus 2 comma minus 1, then minus 1 comma 0, 0 comma 1, 1 comma 4 and 2 comma 9. Then b of x is evaluated at same x values, that is resulting in 9, 4, 1, 0 and 1. These are the value representations of the polynomial. And this is the key idea in FFT based multiplication, that is transforming from coefficients to values and multiply the values directly, then convert back. Each x, y pair is a point on the graph of the polynomial. So now let's move on to the next slide, that is multiplying the value pairs of ax and bx pointwise. So c of xi is equal to a of xi into b of xi. So here the resulting values we obtain are 9, 0, 1, 0, 9. From this you get the value representation of c of x, that is minus 2 comma n, minus 2 comma 9, minus 1 comma 0, 0 comma 1, 1 comma 0 and 2 comma 9. So instead of polynomial convolution, we just multiply the corresponding values. The statement, that is, multiplication in the value representation, is only O of d factorial, which highlights that how efficient this is compared to the traditional O n square multiplication. Now let's move on to the next slide. This slide shows a flowchart style summary of the process. The first step is start with the coefficient form of Ax and Bx. Then we use the fast Fourier transform to convert to value representation. Then the third step is multiply the values pointwise, and then we'll apply the inverse fast Fourier transform to convert back to the coefficient representation of c of x. Now I would like to summarize this entire slide in short. That is, this slide outlines the entire FFT polynomial multiplication pipeline. The FFT and inverse FFT, these are having a good time complexity.
Okay, so now the important question would be, how do we go from coefficient representation to value representation, right? So this process of going from coefficient representation to value representation of any polynomial is termed as evaluation. Okay, so let's say that we have got a d degree polynomial and we need to evaluate it at n greater than d plus 1 points, which means essentially any polynomial could be represented by d plus 1 points. So we need to sample those d plus 1 points, right? So how would we go about sampling those d plus 1 points? So one way to approach this problem is to choose random numbers of x, like let's say I'll sample the polynomial at x equal to 1, then x equal to 2, x equal to 3, x equal to 4, so on and so forth, right? I'll do d plus 1 times and I'll get all my d plus 1 points, right? If I sample at these random points, or I could choose any other random points, right? So this is one way to approach the problem. Actually, there is one problem with this approach, right? Evaluation of each point would take d operations, and for n such points, the time complexity would be huge, right? So, as I said, if I want to evaluate the value of the function of this polynomial function at, let's say, x equal to 1, then I need to substitute that value of 1 in the polynomial, then perform all the d operations, and I have to do those d operations for n such points. So actually, the operations would be n times d. Given that the number of points has to be at least d plus 1, then the operations would be of order d square plus d, which is of order d square, right? As I have said over here. So the run complexity essentially becomes order of d square. So even sampling the points is actually having a greater time complexity of d square. So can we find a way to optimize this, right? We need to choose a smarter way of choosing points such that our time complexity is reduced, right? So let's try another approach. Let's say that we take an odd function, right? Now, an odd function has a specific property that if you substitute minus of x, you get negative of p of x, right? So p of minus of x is negative of p of x. What that essentially means is that let's take a simple function of p of x equals x cubed, right? So you substitute x equal to 1, the value you get is 1. You substitute x is equal to 2, and the value you get is 8, because obviously 2 cubed is 8. Then you substitute x equal to 3, you get 27. For 4, you get 64. Similarly, for negative 1, you get negative 1. For negative 2, you get negative 8, and so on and so forth. So if the input value is negative, the corresponding output value would also be negative, right? Same goes for positive. If the input value is positive, the corresponding value would be positive. Let's take another example of even functions. So for even functions, again, I'm picking the same points as example. I've taken 1, 2, 3, 4. For 1 it is 1, for 2 it is 4, for 3 it is 9, for 4 it is 16. For negative points, it is still the same, right? Because any negative number squared is equal to that same number squared. It doesn't make a difference. The negative sign doesn't make a difference, right? So what I'm essentially trying to say here is that if you got information about the y coordinate of all the x coordinates over here once, then you can automatically derive information about all the corresponding negative x coordinates, right? We just need to be aware of the nature of the function. So here, instead of me evaluating 8 points, I've just evaluated 4 points and I've got information about the other 4 points. Because essentially we are taking advantage of the symmetricity of the function about the y-axis in both cases, right? For both even and odd functions. Now, how can we extend this idea to a general polynomial? So let's take an example over here. Let's take this 5-degree polynomial, and I want to evaluate this polynomial at, let's say, certain number of points. Okay, at n by 2 points if it is an n-degree polynomial. So what I'll essentially do is I'll split this polynomial in such a way that I have got the even function separated over here, and I've got the odd function separated over here as well. Okay. So this even function part would have all the even powers of x, right? So it would have 4, then it would have 2, and it would have 0. Okay, 4, 2, and 0, and all the odd powers would be separated over here as well. I've just taken x as common, so that this inside term also resembles the even function form. Now this is the odd part of the polynomial because it includes all the odd powers. So this is odd function of polynomial, this is even function of the polynomial, right? So I've just written the polynomial in a smarter way here, right? Now, what you essentially get is two new subproblems, okay? Two new subproblems to solve, okay? These inside the brackets, what essentially you have is polynomial of x squared of even part and polynomial of x squared of odd part. So you have to evaluate these two polynomials, these two smaller polynomials at lesser number of points. So these are 2-degree polynomials, okay, which is a much simpler problem than our original problem of 5-degree polynomials. So let's generalize the idea and say we have n minus 1 degree polynomial to be evaluated at n points, right? So those n points are obviously going to be positive negative paired. So you just actually need to evaluate the polynomial at just n by 2 points, right? And the other n by 2 points would be the negative values of those n by 2 points, right? Like 1 minus 1, 2 minus 2, right? So you just evaluated by this half, the value for this negative half is obtained automatically due to the special properties of even functions and odd functions. So I've just written it here in a box. I've just said that if you input a negative value, right, only the odd function part would become negative, right? Else everything would remain the same as even functions. The negative value input does not make any difference. The actual value is just going to be the same, right? So here we get two smaller polynomials. One is even polynomial, other is odd polynomial. They have a degree of n by 2 minus 1. And we can repeat this step and divide this polynomial further into two parts, that is even and odd. Okay, and we can further apply the same dividing approach to the polynomials that we get further down until and unless we reach to a single value, right, where the polynomial size is just reduced to 1. Okay, so we can develop a recursive algorithm that reduces the time complexity of a computation, right? We can say that, okay, we've got an n minus 1 degree polynomial. It is evaluated at n by 2 points that are positive negative paired. Obviously, it's a total of n points. Then we further evaluate these small polynomials, that is even polynomials and odd polynomials generated by splitting this p of x. Okay. But there's one problem that we encounter at the next level of evaluating p of x squared of even part and odd part. What is the problem that we obtain? See, these all points are positive negative paired, right? At the first level of recursion. But at the next level of recursion, when we obtain these points from even part and odd part, these are squares, right? Now squares are always positive. So these points, these endpoints are not positive negative paired. Only these endpoints are positive negative paired. At the next level of recursion, where the size of the polynomial is n by 2, right? These n by 2 points are not positive negative paired. Actually, the size of the polynomial is n by 2 minus 1. So you have to evaluate at n by 2 points. and these points are not positive negative paired. Now, can we make this new set of points positive negative paired, right? This is only possible if we expand the domain of initial set of points to complex numbers. So let's understand with an example. Let's say we've got this polynomial, right? It's obviously having a degree 3, so we have to evaluate it at 4 points, right? So let's see what points can we pick, right? So we can either have 1, okay, let's say, and we would have a minus 1. Well, 1 squared is 1, minus 1 squared is 1. So yes, we have 1 at the next level of recursion. What other points can we choose for x2? Okay, so I want at the next level that this x2 squared has to be negative 1. Now, what number squared is negative 1? Well, as far as I know, an imaginary number squared is negative 1, right? So this has to be I, as a definition of I is square root of 1. So I squared would obviously be negative 1. Similarly, negative I the whole squared would also yield negative 1. And at the last level of recursion, we will have 1, right? Because x1 squared is 1, so its squared is 1, and negative 1 squared is 1. So we need to expand our domain to the imaginary numbers, and that's what I have done. That these points would be 1, minus 1, I, minus I. At the second level of recursion, again, they are positive negative pairs. And at the last level of recursion, we reach the same value. So the 4 points need to be plus minus 1 and plus minus I. We can say these points are a solution to this equation x to the power 4 equal to 1. So we can say that these points are fourth roots of unity. Now, let's take an example for a greater size polynomial. Let's say it is having 8 terms. So what would be the 8 points that you would need to sample that would be positive negative pairs? So again, they would be eighth root of unity. So 8 roots of unity you need to use to sample all those points. So these would be the values of points that you would sample, which at the next level of recursion would again yield you the same value, and this would again yield you the same value. And at last you get this value that is 1. So understanding roots of unity. So the concept of roots of unity is quite simple. You get a unit circle, so you have a unit circle, and each point on that unit circle is a complex number represented by this form. This is Euler's identity of representing complex numbers. That you can represent complex numbers as the real part is represented by cosine of theta and the imaginary part is represented by sine of theta. Okay, and theta is the angle that is subtended from the vector of complex number from the x-axis. Okay, so this is the basic definition. And nth roots of unity are represented by this. The general notation is omega is equal to e to the power 2 pi I by n. Right, so we actually need to evaluate this polynomial at n minus 1th roots a total, right? So this would be a total of nth roots of unity. Okay, so if the polynomial is of size n minus 1, we need to evaluate it at nth roots of unity. Okay. And why does this work? Essentially because the positive negative pairs are obviously always going to be present opposite to each other. Okay. For example, you see here 1 minus 1 present opposite to each other. There is a difference of like theta of 180 degrees every time. Here this is, plus I, this is minus I. So difference of pi radians, right? So similarly, any corresponding point on the unit circle, the corresponding negative point would be present at pi radians. Therefore, you can say that the negative corresponding negative value of the jth root of unity is going to be j plus n by 2. So this is the fast Fourier transform algorithm where we define an input array of length p, and we say that if the size of that array is 1, then we return the same value. If not, then we define the roots of unity, and then we define the odd polynomial and even polynomial arrays. Okay, and then we define uh, the recursive step of the algorithm where the function is called on the even part and the odd part, and the corresponding size of empty array is created, and how this empty array of outputs is going to be populated is decided by these statements present inside the for loop, and the array is then returned. And this step is repeated again and again until the final solution is obtained. Then we see how the FFT algorithm is implemented, where we've got this polynomial. It is split into two parts. Then these parts are evaluated, and then we return the base case. Once the base case is returned, all the other parts are evaluated according to the algorithm. This is a very basic example of how it is done, and we reach the final solution. Okay. Next, we discuss the time complexity. So the time complexity analysis of this algorithm is solved by two parts. The first part is done by substitution, where I evaluate the time complexity by substituting the values of n at different levels. And then finally, I get the reduced time complexity to be n log n. If I do the same thing with the recursion tree method, I get the same time complexity of uh, n log n. Essentially, the value of k is log n, k is multiplied by n because you're evaluating total cost. So the total time complexity is still n log n. Now, an alternative perspective to the evaluation of FFT is that it can be represented by this matrix where these are going to be roots of unity, different powers of roots of unity for an n degree polynomial multiplied with the coefficients to generate the output values over here. Again, this we can talk about interpolation as the inverse of DFT. So the inverse FFT operation is known as interpolation. Just as the FFT operation was known as evaluation, the inverse FFT operation is going to be known as interpolation. And this is the difference between um, the FFT matrix and the inverse FFT matrix. Every term is just replaced by a negative power and a factor of 1 by n. That's it. And here is a small linear algebra proof of how do we actually achieve the inverse DFT matrix. Well, that is not quite important from an algorithmic perspective, but you can refer to this if you are interested in actually knowing how the inverse DFT matrix is obtained. Okay, now we move on to the final part, that is comparing the FFT algorithm and the inverse FFT algorithm. Just one small change is there. Just you need to change the omega value. Right here, the power is just negative, and you're multiplying it by a factor of 1 by n. That's it, and you get your inverse FFT algorithm. Now, what do we do when the number of terms in the polynomial is not in the power of 2, 3, or 5? Well, we perform zero padding. Zero padding essentially means you are adding zeros in your coefficient polynomial array such that the number of terms in your array are going to be in power of 2, and then you apply the FFT operation on that particular array to get the.
So now we will be looking at the code for FFT and inverse FFT. So first we include all the necessary libraries. We are using vector, complex and maths libraries, and this code is in C++. The function FFT takes a vector of complex numbers as input and process it recursively. Here the for loop adjusts the value of a0 and a1 to get the FFT result, applying the FFT formula. Here is the loop. Then compute FFT. This compute FFT function converts the polynomial coefficient. Here's the polynomial coefficient. It is converted to complex number and apply the FFT to them. Then the multiply value representation. This function multiplies two polynomial in the value domain by performing element wise multiplication. Here's the multiplication. Then the display values. Display values. It by a for loop shows all the values. Next, the program asks the user to input the number of coefficient. So here's a number of coefficient. Then the FFT of both polynomial is computed using compute FFT function VH, what we have seen above slides. Then finally two polynomials are multiplied in the value domain using multiply value representation. That is also what we have seen above. So here's the output, number of coefficient given by the user. Then here's the two polynomial value representation of first polynomial, and this is the second polynomial. And after multiplying using the formula we defined, here's the answer of the product polynomial. So now we will be looking at FFT inverse. Same concept of FFT, but there are some changes. So the inverse FFT logic is it divides the complex number by 2 and solve it recursively. So first it calls the FFT function. It calls the FFT function of the values with the invert flag set to true to apply the, here's the inverse flag to compute the inverse FFT and return the coefficient. It first calls the FFT function on the values with the invert flag set to true to apply the FFT inverse. After it converts the complex result into integer coefficient using rounding. Then it takes the computed coefficient from the IFFT values and prints them into a readable form showing the final coefficient representation of the product polynomial after applying FFT and IFFT, inverse FFT. So here's the input, number of points 8 user has given, and here's the 8 complex number, and here's the product polynomial output. So now what we have discussed was the algorithm for power of 2, but radix q FFT extend this to the power of other prime number such as 5, 7, 3, etc. for a polynomial of size q to the power k. The algorithm divides the problem into q subproblems like q to the power, so qq problems, subproblems, in each recursive step, efficiently reducing the complexity. The time complexity is expressed as this, which represent a recursively breakdown of the problem. So here the problem is breaking down into q parts, and each part is buff n by q. Like if we write n by 2 like this, so each problem is divided into 2 parts, each of n by 2. So what it is representing, and this simplifies to O, big O of log q n, which is a logarithmic time complexity, which is much more less than the previous algorithm. For polynomial given like this, we split into 3 components. Here's the 3 components, where p naught x power 3 contains coefficient at index I equals to 0 mod 3, here's I equals to 1 mod 3, and I equals to 2 mod 3. So here's the example for that. Uh, so we split it into like this two parts, three parts, sorry, and we compute the following values. So this reduce the problem size by a factor of 3. So it would be like this. Now here's the algorithm for this. The main aim is to the values are then combined using the roots of unity specific to radix 3, which reduce the problem by a factor of 3 in each recursive steps. Here's the three part, dividing into three part, and the FFT result for P0, P1 and P2 are combined using the respective roots of unity here in the loop. So here's the difference between radix 2 and radix 3. Radix 2 uses two roots of unity, and radix 3 of course uses three roots of, like here there are two parts, here are three parts, two roots of unity, three roots of unity. This is just an example to explain difference between them. So after we are putting the value in radix 2, here this value, there are two parts, even and odd, 5 and 7, just a convention. And after using the formula and from the function, this is the values.
Now, we can easily perform the radix to FFT on the coefficient array if it is padded with zeros, right? Because you easily know that the number of terms are going to be in power of 2. So you can simply perform the radix to FFT. That means that you're dividing every sub-array in two parts at every level of recursion, right? That means radix to FFT. But this method of zero padding is inefficient for large sizes of polynomials, which have a number of terms not in power of any number of primes, right? So 2 is a prime number, obviously, and this divide and conquer technique can be applied to uh, the number of terms of a polynomial that is having a power of any kind of primes. It could also be having a power of 3, let's say 3 square, for instance. You can divide the polynomial into three parts at the first step, and at the next step, again, you divide the polynomial into three parts, and you get your solution. Okay, so similar to when the power is in terms of 2, where you're dividing in two parts at every level of recursion, right? So this can be done for all the primes. Now, if you were to perform the zero padding technique to the next nearest power of 2, let's say that the number of terms of the polynomial are 540. Now 540 is not purely a power of 2 or any other primes for that matter, right? If you were to perform the zero padding technique to the nearest power of 2, then it would be 1024 in this particular case. So we would need to add 484 additional zeros to the coefficient array, and that is quite an inefficient process, right? So what can we rather do is we can figure out the prime factors of 540, and then we obtain this power of 2, power of 3, and 5. So we can perform radix 5, radix 3, and radix 2 FFT for a more efficient computation. Okay, so we follow the mixed radix FFT approach, where the size of the polynomial n is not purely in size of power of any prime number like 2, 3, 5, 7, etc., then it can be factored into smaller numbers, and we can break it down into smaller FFTs of different radices. Okay, the mixed radix FFT generalizes the Cooley-Tukey FFT algorithm to handle arbitrary composite n by decomposing n into smaller factors, where n is the number of terms in the polynomial. Okay, so if n can be factored into, let's say, these many primes, then the mixed radix FFT decomposes the computation into smaller FFT of these sizes. Okay, this reduces the computation time compared to padding zeros to the next power of 2, which was quite an inefficient process. The time complexity calculated for these all factors is going to be order of log n. So considering our previous example of 540 terms, if I were to pad the zeros, I will get 1024 terms and the number of operations would be 10,240. Whereas if I use the mixed radix approach, I can get the computations to be done in around 3,240 steps only. So that is the magnitude of reduction in time complexity that you see. Okay, so now let's take a simple example of mixed radix FFT to understand how it works. So I've taken a polynomial over here that is having about six terms. Okay, and here 6 is neither a power of 2 nor a power of 3. Well, it can be factored into 2 times 3. So we need to perform a mixed radix FFT over here in this case, right? Which is going to result into efficient computation of the discrete Fourier transform. So now I can follow two approaches. Either I can divide the subproblem into two parts further on and then three parts, or I can divide the subproblem into three parts and then two parts. Well, let's try the first approach where I divide it into two parts and then three parts. Well, then accordingly I perform the radix 2 FFT at the first level of recursion and radix 3 FFT at the second level of recursion. Okay, and I accordingly use the radix 3 FFT algorithm, which is quite similar to the radix 2 FFT algorithm, just that in this case you would call FFT on three subarrays than on two subarrays that we saw in radix 2 FFT. So here the subarrays on which FFT is called is 3, and the for loop runs for n by 3 up to n by 3 times, right? And there are going to be three lines of updation because firstly in the radix 2 FFT case we were just considering two pairs of roots, the positive negative pairs, right? But in radix 3 FFT you need to consider three set of roots, okay, of the unit circle, three set of roots, okay, or three roots of unity. So I perform the operations and computations and I get the resultant array value, and then I go to the next level of recursion and get the final solution further on, okay, where my final solution is this. Therefore, we obtain the value representation with the mixed radix FFT approach. Now let's try approach 2 where I divide the problem into three parts and then I further divide the subproblem into two parts. And we apply the same approach here, just that here in the first level of recursion we apply the radix 3 FFT, and the second level of recursion we apply radix 2 FFT. Okay, now we apply the same process of applying the algorithm, finding the answer, and then we get the same result finally after many computations. So it doesn't matter the order in which you apply the radix FFT, either you apply the first uh, uh, 2 times 3 radix approach or 3 times 2 radix approach, the final answer would yield the same value with same time complexity. So that is my presentation on how can we use mixed radix FFT approach to actually make efficient computations.